Survey of Calculus, Chapter 6, Section 3, Maximum Minimum Problems. Now we've seen maximum and minimum problems before, but this time we're going to be dealing with multiple variables, and this is where that three-dimensional graphing is going to come into play. Again, you're not going to have to actually do it, but it helps to be able to visualize it. So first of all, a function f of two variables has a relative maximum at AB if the function x of xy is less than the value of the function at AB for all points in a region containing AB, and has a minimum if f of xy is greater than or equal to f of AB for all points xy in the region containing AB. I'm going to show you what that looks like here. Again, we're thinking three-dimensionally, so here's an example. You've got this point that is obviously, it's like a mountaintop, and it is obviously higher than anything anywhere around in any direction, and so it is a relative maximum. And then you see over here we've got what looks like a funnel, and again you've got a relative minimum. There are no points anywhere near there that are lower than that point in any direction, so you have a relative minimum. And it's the same idea as we talked about with two-dimensional graphs. It's just that now we're really talking in terms of an actual physical height in that third dimension, or a depth. So same idea. You do have to consider the points in every direction around. Here's another example. We got some relative and absolute maximums and minimums here, just like with a two-dimensional graph. And again, notice that the maximums are kind of like mountaintops. They're higher than any other point in the surrounding vicinity. And the minimums, again, they're kind of like the bottom of a funnel. Nothing goes lower than that. Things that are called saddle points. And it looks kind of like that here. If you look at this, when you look at it from one perspective, from the red, where that red curve is, it looks like it's a maximum. But if you look at it in terms of that blue curve, it's a minimum. In reality, it's neither. It's what's called a saddle point. And you should be able to see from the shape of that why it is called a saddle point. This is not a maximum or minimum, but it can, it's something we need to watch out for when we're trying to find maximums and minimums. Saddle points can initially appear to be that. And so we're going to have to make sure that we test and make sure what we've got is not a saddle point, that it is a true maximum or minimum. So we're going to be working with problems where we need to find the maximum or minimum values. We'll need to determine what points are potential maximum and minimum points, and then we'll test to make sure that they really are. After we test it and confirm it, then we'll put the points into the function and find the actual max or min value. So before you would find x, you would make sure that it actually represents a max or min, and then you would put it into the function to find y. This time you're going to have x and y, and you'll confirm that x and y, where they are, will represent a max or min, and you will put those into the equation to get z, which will be the actual value, the actual height or depth of that point. So we have what's called the d-test, and if f is a differentiable function of x and y, to find the relative maximum and minimum, what we have to do is we're going to find the partial derivative of x, the partial derivative with y, the double partial derivative with x, xx, and f yy, and f xy. So we're going to find these partial derivatives, and then those the two, for one for x, one for y, and the three second order ones you see there. You don't need yx, you just need xy. So you're going to find those first and write them down. Then you're going to solve the system of equations. You're going to set f of x, the partial derivative with respect to x equal to 0, the partial derivative with respect to y equal to 0, and then you're going to get a solution for those. You're going to get AB that solves both of those. Then you're going to evaluate D, and how you evaluate D is you take the second order partial derivative f xx and you put in AB. You take f yy and you put in AB, and you'll multiply those two numbers together. It will give you numbers. And then you're going to subtract f xy at AB squared. Now, it looks really complicated, and it would be easy to get confused, but if you take this one step at a time It's really not as complicated as it looks. These formulas are on your formula sheet. Okay, now here's the deal. If D is greater than 0 and f(xx), the second order partial derivative, is less than 0, then you have a maximum. If D is greater than 0 and the second order partial derivative is also greater than 0, you have a minimum. So D has to be, first of all, D has to be greater than 0 to have a max or min, period. If the second order partial derivative, the xx, if it's negative, you have a maximum. If it's positive, you have a minimum. If D is negative, you don't have either. You have a saddle point. And if D is 0, the test doesn't work. And I'm pretty sure we're not going to deal with any of those. All right, so we're going to find the relative max and min for these. Now remember the 4 steps. If you do this in an orderly way, it's going to make life so much easier. You're going to find the partial derivative with x and y. Then you're going to find the second order xx. You're going to find yy and xy. So find all of those first. Set the partial derivative of x and of y equal to 0 and solve them together. And then from there, you're going to put the result into D. Okay, D has to be positive. If it's negative, you have a saddle point. If it's positive, and the result and f of xx is positive, you have a minimum. If it's negative, you have a maximum. So go through those steps, pause the recording, give this a try, and resume to check your answer. Okay, so there we have our partial derivatives, all 4 that we had to find. It helps if you solve one of these for either x or y. I would solve the second one. Substitute. And then find x. So we have 2, -1 as the only point that's worth testing, the only point we have that's a critical point. Now we want to see if it's a saddle point or an actual max or min. So we're going to find D. And they took the equations we got for those second order partial derivatives and put in 2 for x and -1 for y. And solving, we get 3. So D is positive. And f, the second order partial derivative xx, is also positive. Since they're both positive, we have a minimum. Now we're going to take 2 for x and -1 for y, and we're going to put it into the function to find out what that minimum value is, and we get -3. So at the xy point, 2, -1, the z value is -3. Now try this problem. Pause the recording, give it a try, and resume to check your answer. Okay, so we have 4, -1 as our critical point. Now we're going to try, we're going to use D. Since D is 7 and f, second order partial derivative of f with respect to x is 2, they're both positive, we have a minimum value. Now we're going to put 4, -1 into the original function and discover that that minimum value is -14. Well, let's try another one. Pause the recording, give it a try, and resume to check your answer. As I go through these, you may want to pause and look at what you did. Not just check your answer, but if you made a mistake, see if you can find the mistake. The problem with these is if you make a mistake early on, you pretty much had it for the rest of the problem, which is why showing your work is going to be so very important, especially on tests and quizzes. Now we actually have two values for x here. And we find both values of y, find the matching values of y. So we're actually going to need to do two tests, because we have two critical points. So we're going to do D for both. First time we get a -1. Now remember what that means is that it's a saddle point. So we don't have a max or min at 0, 0. Putting in those lovely fractions, we get 1, which is positive. So since 0, 0, we get a -D, we have a saddle point. At 1, 6, 1, 12, we get a positive D, and we get a negative f second order derivative with respect to x, partial derivative. So we have a maximum at 1, 6, 1, 12. Putting those into the function, we get that that maximum is 1 over 432. And not much of a maximum. The graph must be pretty small. Pause the recording, give this a try, and resume to check your answer. Again, pause as you need to see what you did, to find any mistakes and correct those, and then resume when you're ready to move on. Notice with both of these, you're actually just solving each of them individually for one variable. So that gives us two critical points, 1, 2, and -1, 2. And we will test both using D. And we get 12 using 1, 2. And we get -12. Okay, so what that tells me is that at 1, 2, we do have a max or min. And in fact, we have a minimum because D is positive, and f second order derivative partial with respect to x is also positive. When D is negative, as it is for negative, so we have a saddle point at -1, 2, and we have a relative minimum at 1, 2, and that relative minimum is, okay, this is a similar problem, but it's just a word problem this time, but we're going to do the same thing. Let's see, they want us to find how many of each type must be produced and sold in order to maximize profit. So remember, profit is revenue minus cost, and that's what we're trying to maximize. So you're going to want to find that function first and then run it through the procedure we've been discussing. Pause the recording, give it a try, and resume to check your answer. So first we find our profit function and simplify it as much as we can, just to make life easy. And then we find all of our partial derivatives, first and second order. Solve the system of equations. Adding the two equations, we get -2x plus 8 equals 0. There's different techniques you can use, so you don't necessarily need to do it exactly the way they do. As long as you come up with the same answer, you should get x is 4 and y is 2. So we will test 4, 2, putting it in for D, into the formula for D. We get 4, so we have positives, and we have that D is positive, and we have that P XX is negative, so we have a relative maximum at 4, 2. Putting that into the original equation, we find that they must produce and sell 4,000 of the $3 golf balls and 2,000 of the $2 golf balls, and they will make $13,000 to maximize their profit. Okay, this is the section summary. Pause the recording and look over it. Resume when you're ready to move on to additional practice. As you go through these, pause the recording, give them a try, and then resume to check your answer.